All right, part two of basic scientific literacy for adults. And again, people who are not adults are welcome to watch it, but it's not primarily for you. People who are studying for their GEDs, you're welcome to watch it, but it's not necessarily going to be what's on the GED. Finally, those of you who have more knowledge than what I'm about to present, certainly you're welcome to watch this, but it might take away from whatever other learning you would be doing. But by all means, watch it, critique my style. Finally, those of you who have religious issues with the idea that the Earth travels around the sun, please don't watch this and take that up with somebody else. I don't want your PMs or anything like that. I know I was shocked to find that there were people who still believe in geocentrism. Give me a break, okay? All right, let's review some basic facts. The sun has about 99.8% of the mass of the solar system. So by definition, the sun is the center of the solar system just based on the fact that the sun exerts the most gravitation. The sun will pull the other objects in the solar system towards itself, okay? The sun is huge compared to the Earth. If the Earth had the diameter of a penny, the sun would have the diameter of 6.7 feet. Now, the sun is also very far away. If we were to shrink the Earth to the size of the penny, the sun would be 242 yards away. And it actually takes light from the sun about 9 minutes to get to Earth. And that's because light has a fixed speed. So when you look at the sun, and please don't because you'll protect your eyes, but if you have a welder's glasses or some kind of protective eclipse viewer where you can look at the sun, you're actually viewing the sun about 9 minutes ago. So just a little fun fact there. The planets are arrayed around the sun in such a way that as you move further out, you go Mercury, Venus, Earth, Mars, Jupiter, Saturn, the distances between the orbits of the planets get greater and greater and greater until you get to, let's just say, Pluto. Pluto's not considered a planet anymore, but Pluto would be about 40, I believe about 40 astronomical units out. Okay, so astronomical unit would be the distance between the Earth and the sun. So, but the sun really steals the show. I mean, even Jupiter and the heavy gas planets are minute compared to the sun. So the sun exerts the gravitational influence that will tend to pull the planets towards itself. And so by definition, really, the sun would have to be the center of the solar system. Now, first skeptical question that I will address. And that first skeptical question will be, hey, CHistrue, wait a minute, you're saying the Earth is pulled towards the sun. Why doesn't the Earth just go into the sun? Why does the Earth stay in an orbit? Well, I have it right here. The Earth is more or less in what we would call a almost perfect circular orbit. It's actually elliptical, okay, where the sun would be, ellipses have what are called foci, going a little too far there, but the sun would be in one of the foci of the ellipses. But we're going to kind of pretend that Kepler never existed and that the Earth is in a perfectly circular orbit to just make this simple for now. Okay, in a perfect circular orbit, here would be the Earth and here would be the sun. The Earth is being pulled towards the sun by a vector that we'll call gravity. Okay, so this is the centripetal force, okay, or the force pulling towards the center. And then, yeah, sure, if we just let the Earth go, the Earth would fall into the center of the sun. But we have another force, which would be the centrifugal force, or the force pulling away. And that's left over from the origin of the solar system. Okay? Now, the balance of these two forces would be an orbit that would be almost perfectly circular, going in a clockwise direction that's going to keep on going and going and going. That's the perfect balance between the two forces. I mean, if you look at this, and then you have the Earth moving around a little more, a little more, a little more, a little more, and then it takes a year for the Earth to go completely around the sun, okay? And so, there we go. What you have is you have a perfect circular orbit that would be the balance of these two vectors, okay? Now, why don't we feel it? Why don't we feel ourselves? Now, see, that'd be the next skeptical question here. If we're being pulled towards the center of the sun, if we're being pushed away from the sun, and also if you have, think of the Earth as a ball spinning on its axis. Okay, that would be the rotation of the Earth that happens once a day. So the orbit of the Earth around the sun happens once a year. The rotation of the Earth happens once a day. And incidentally, the moon goes around the Earth once every lunar month, which is approximately 1 month, about 28, 29 days, somewhere in the, not an exact number, but somewhere between. So again, you then have a question of, gee, okay, I can understand how the moon would go around the Earth because I'm not moving relative to the moon. The moon is, well, let's put it this way, the moon is orbiting the Earth, and the Earth is the more gravitationally massive object. So that makes sense, CH is true. But if I'm rotating, if the Earth is rotating, why am I not being flung off the Earth? If the Earth is moving around the sun, why am I not also being flung off the Earth into space? The answer is that as these various forces act on the Earth, they're acting on you also. The gravitation of the sun is pulling the Earth in, but it's pulling you with it. The centrifugal force is acting on the Earth, but it's also acting on you. Now, maybe as the Earth orbits the sun, well, definitely as the Earth orbits the sun, there is a slight change, and that might produce a might bit of an overall net force that would be acting on the Earth, but be acting on you also. Okay. Now, as the Earth is rotating, you also have, think of a spinning ball. Okay, you would also have that same force, and you notice those of you who are marksmen, you have what's called the Coriolis effect, where you have to take into account the rotation of the Earth. However, and that's a slight force, but we don't really even feel that, because as the Earth is rotating, well, let's put it this way: there's a force that is centrifugal, that is pushing you off the Earth. The Earth is moving with it. Okay, so the Earth, in a sense, is moving under your feet with you. And that's an important principle in the universe, where there is a certain degree of, even before Einstein, they understood that a lot of motion is relative. That if the Earth is moving and you're moving with it, it's like driving in a car. That'd be a great example. You're driving in your car, the car's going at 70 miles an hour, but you're moving with it. So you feel that little bit of acceleration from 0 to 70, and hopefully it's 65 because that's the speed limit, but all right, we're all human, right? So as you're going from 0 to 65, you're feeling the acceleration, and that's like a force moving you backwards. But it's not strong enough to fling you out of the car, all right? So, and then eventually you're in a stable velocity where the car is moving and you're moving with it until you slow down. And these laws of motion eventually led, by way of Isaac Newton, led to a great deal of what we would call modern-day physics, where we eventually had to accept the fact that there is no up or down. That's defined by gravitation. And there is no really such thing as stationary. It's stationary with respect to a given object. Now, in part 3, I'm going to try to clear up some loose ends on the solar system, and I'm going to maybe try to move on to some other subjects. Hold on.